Hello everyone, so welcome to today's webinar. So like Sarah said, today's presentation title is on unlocking the values in big data and the benefit of using advanced modeling techniques. So before we start off with today's presentation, I would just like to give you a quick general overview on what we will cover in today's talk. So I'll start off with a brief introduction and some motivation as to why we're using all these advanced data-driven model and modeling techniques to analyze our data. And then I will introduce to you different types of modeling techniques. So for the purpose of this webinar, I have broken this down into basic modeling technique, intermediate modeling technique, and advanced modeling techniques. And then I'll go on to talk more about, how can we tackle labeled data versus unlabeled data, and what sort of modeling technique we will need to use if we encounter these type of data sets. And then I will emphasize on the benefit of using data-driven model through two different case studies. The first one is on the detection of a magnet focused on the Coriolis meter. The second one is on the detection of an unwanted second phase in the ultrasonic flow meters. And then I'll wrap up today's presentation off by just giving you a quick conclusion and a quick summary on what we have covered in today's talk. So without further ado, let's start off with some introduction and some motivation. So in flow measurements, flow meters such as the ultrasonic meters is capable of outputting a large number of data, which provides valuable information that tells you the operating conditions as well as the health of the flow meters. So any potential measurement errors can be detected in drifts seen in both the individual and the combination of digital process values. So any errors we may have with the flow meters, then these are usually manifested through drifts in certain diagnostic variables. So you may think, well, that's great. If we have a problem, we just need to look at certain diagnostic variable and then we can sort out the problem. Unfortunately, things is not so easy. What we actually found is that there's actually a challenge in being able to distinguish between different errors. Some errors can actually incur the exact same type of drift in the same variables. So whenever we do see there's some drifts in the diagnostic variable, end users ended up in a little bit of dilemma thinking, well, what is exactly causing those drifts? Is it because of we have error A? Is it because of error B? Or is it because of error C? So although we know that there's something wrong with our flow meters as suggested by some drifts away from baseline value, we can't pinpoint with great certainty as to, well, which error is responsible for those drifts. In addition, because flow meters is capable of outputting a large amount of data and lots of variables, each of these variables has very complex multiple interrelationship with each other. So without using modeling techniques, it's actually very difficult to fully understand the correlation between different variables, try to dissect, the relationship between all the variables. So for example, if we see a drift in variable A, does that mean that if we can find the error that's responsible for the drift in variable A, we have solved the problem? Not necessarily, because a drift in variable A could be a byproduct of a drift in its related variable. So it could be something wrong with variable B, C, D, and F. So we need, in order to properly understand the data and to digest, what's actually happening, it's important we look at, all the variables. So with the help of data-driven model, we can achieve that because data-driven model can analyze the relationship between process variable under different operating conditions. It can also help end users to extract key variables, for example, indicate to end user which variable are the most likely to be affected when exposed to certain operating conditions, so that end users can focus on key variables as well as without having to pay much attention to other redundant ones. It can obviously be used to perform error detection as well as making future prediction. Through the use of data-driven model, we can actually overcome the ambiguity issue arise from drifts we've seen in diagnostic variable as well. So next, let's look at the different types of modeling techniques as available to end users. So there are many different types of modeling techniques available to end users to extract different levels of insight from data. The more advanced the model, then obviously the more insight can be extracted. And however, because we're dealing with a more advanced model, then we require more from our data as well. So there's an increasing level of details on the data source are also required if you're dealing with more advanced model. So for the purpose of this webinar, I have broken down the modeling technique into 3 categories, so then I can demonstrate to you better, the type of modeling techniques available and the levels of insights we can get from them. So let's start off with the basic modeling techniques. So basic modeling techniques is a very good tool that will able to give you a quick overview on what your data is like. So the overall data distribution, the data structure. So example that goes under this type of basic modeling technique would be things like correlation plot, box plot, interaction plot. The next one up is the intermediate modeling techniques. So now we are doing a little bit more. So example of that would be like regression analysis, time series prediction, as well as using algorithm to detect any sudden spikes and sudden changes in your data, which could signify to end users, maybe there's some potential underlying problems. The next one up is the more advanced modeling technique. So this is when machine learning models, such as the classification model goes in, anomaly detection, as well as the ability to extract key variables amongst, a group of maybe 60 or 70 variables to pinpoint to end users which are the most important variables we really should be focusing on if end users wish to monitor a particular type of error. So in the next couple of slides, I'll look at each of these categories in detail, as well as showing you some examples to see the level of insight we can obtain from each of the modeling techniques. So let's start off with the basic modeling techniques. So because this is a basic modeling techniques, there's not much requirements from the data, so this can be applied to all data types. So this type of techniques is extremely useful if you wish to look at, a bigger pictures on the data structure or your data distribution. So imagine you're dealing with a big data set, then having a good, by using a basic modeling techniques, you can get a general overview on what your data is like. Because if you don't know what your data is like, how can you perform more complicated analysis on your data? Basic modeling technique can also be used to, analyze the relationship or investigate the relationship or the correlation between variables. So again, this is extremely useful if you're dealing with lots of variables. So maybe it will be quite easy task if you say you only have 10 variables, but imagine you're having like 40, 50, 60 different variables. It's going to be really time consuming if you were to do this by hand. But by using a basic modeling technique, this can be done very quickly. It can also be used to give you an easy comparison on the meter's performance under different conditions so that you can compare to see, well, how does my meter perform in different conditions so that you can find its optimum operating conditions. And because this is a very basic modeling techniques, then the level of insight is obviously quite elementary. So let me now show you some examples which will go under the basic modeling techniques. So here is an example of a box plot. So I'm sure you're all aware of box plot. So in here, we're dealing with 4 different types of meter A, B, C, and D. And we have plotted the box plot for 6 different diagnostic variables. So by producing something just as simple as a box plot, it's able to tell you the overall data structure and the data distribution of your data, and you can actually make an easy comparison on how each of the meter performs. So for example, if you look at the average velocity graph, from here, straight away, you can very quickly say that, well, it seems that meter A, meter B, and meter D had a very similar data distribution, whereas meter C is the odd one out here. Similarly, if you were to look at the percentage error in volume flow data, and here it appears that meter A is the one that performs the best by showing the least amount of by showing the least percentage error in volume flow, and the data is more condensed and more concise. It's not as spread out. So the width of the box in the box plot tells you how varied your data be. And another thing it can tell you from a box plot is that it can tell you the lower quarter range, the upper quarter range, as well as the median value. So just, a simple box plot is able to already giving you more information, more insight, on the basic structure of your data. And of course, making very easy, simple comparison. The next one is what we call a correlation plot. So a correlation plot essentially measures how correlated your variables are. So, and it's usually measured by what we call a correlation coefficient. So it's just a number, correlation coefficient. So if you have a positive correlation coefficient, then it means that your 2 variable has a positive correlation. In other words, if one goes up, the other one goes up. If your number is negative, then it means it has a negative correlation. In other words, if one variable goes down, then the other variable goes up. So the strength of your correlation, so how correlated your variable is, depending on how close the number is to +1, if you're looking at positive correlation, or how close that number is to -1, if you're looking at negative correlation. So as a quick example, if we were to look at average flow, measure against average gain, then they share a correlation coefficient of 0.97. In other words, they are strongly correlated and it's a positive correlation. So if average flow goes up, average gain goes up. So this simple correlation plot is extremely useful if you're dealing with a large amount of data with lots and lots of variable, because this can actually tell you just very quickly, the correlation between variable, and it may actually give you some new insights that you never realized between two variables. The next one is an interaction plot. So an interaction plot is used when you wish to measure the degree of an impact when you're changing from one operating condition or one condition to another condition. So in this example here, we have two ultrasonic meter, ultrasonic C, ultrasonic D, illustrated by two different colors of line. On the x-axis, we have 8 different operating conditions, and on the y-axis is the mean value of change. So by producing a very simple plot like this, it can tell you how does the performance of the ultrasonic meter change when you change from one condition to another condition, and the way it changed, the direction of the shift as well. So although this is, a very basic modern technique, it gives you a very quick general overview on your data structure, your data distribution, as well as the relationship between your variable. So next, let's look at something a little bit more complicated. We wish to do a little bit more with our data. So now we're on to intermediate modern technique. So because we're dealing with intermediate modern technique, we are requiring a little bit more from the data now. For example, for time series prediction, we will need the data to obviously be collected over a period of time. So in other words, we need a time series data. The longer the period, the more accurate your prediction is going to be. So for example, say we only have a day worth of data and you wish to predict what's going to happen, say, in the next week. Yes, your model can do that. Your algorithm will do that for you. However, the prediction is not going to be accurate. It's going to have a high degree of uncertainty because you're forecasting for a longer period of time and yet you only have 1 day of data. So if you want your prediction to be accurate, then obviously it'll be good if your training data is collected over a longer period of time. The next thing that can go under intermediate modern technique is that we can use an algorithm to detect any sudden spikes, any sudden jumps, any weird structure changes that can occur within your data, which could signify to end users, there's something weird going on here, so that end users can go and check it out. Another features that we can use from this algorithm is that if, for example, after you go check out, you realize, my system is actually working fine, the reason why the sudden spikes and jump occur is because, due to some silly, non-intentional human operational error. If that's the case, you can actually use a type of algorithm to remove those sudden spikes and jump to restore the data back to its expected format. So when will this become useful? Well, it will become useful if you wish to restore expensive data. So, for example, if you have a set of data that was gathered under, using very expensive equipment, it takes a long time to gather, and the experiment is extremely complex. You really don't want to repeat that experiment simply because, it's contaminated by non-intentional human operational error. So this is when you can use actually this type of algorithm to remove those sudden spikes and jump detected if you're certain that they do not relate to any underlying error with the system, and you can restore the data back to its expected format so you can still use it. So of course, this always save time, save labor costs, because you don't need to repeat the experiment again. The data will not go to waste and you can still use them. So again, I would like to show you some examples on the things that you can get from intermediate modern technique. So here, it's just a very simple nonlinear regression analysis. So I'm sure you're aware, regression analysis are extremely useful tools if you wish to analyze the relationship between multiple variables. Regression analysis will usually plot a best fitting line based on the relationship observed with a 95% confidence intervals. So again, in this example, you can always tell that it's a nonlinear regression. The next one is a time series prediction. So here the algorithm, the model is able to predict what's going to happen in the next time period based on the previous trend observed. The next one, so this is the algorithm I was talking about where it can detect any sudden spikes and jumps. So in this graph, the blue line represents the restored value, and the grey line, which is overlapping with the blue line in certain places, represents the original data. Any sudden spikes, jumps, structure changes are then flagged up by the model and illustrated at these red dots. if you really want to look at, the effect of those sudden spikes and jumps, then there's a red graph here, which shows you exactly when those unexpected spikes and jumps, peaks occurred. So by using this algorithm, it then removes these red dots and restore it back to the expected trend that's conform with the rest of the healthy data. So as you can see that when you're dealing with intermediate modeling techniques, we are dealing with more, we can get more information. We can now do, not only we can get a general overview on the data, we are now making prediction, we're making forecasts. So this is the difference between intermediate and basic, whereas basic is just more, a visualization tool that gives you a very quick general overview on what your data is like. So next, let's now move on to the more advanced one. So because we're dealing with a more advanced one, more insight can definitely be obtained from this type of modeling techniques. For example, we can improve fault diagnosis because advanced modeling technique can be used to pinpoint with greater certainty on the error that's causing those unexpected drifts and patterns seen in your data sets. It can obviously help us with decision making. It can minimize unexpected downtime because we can use these type of modeling technique to constantly monitor the performance of your instrumentation or your flow meters to make sure that they're always at their optimum conditions. And because we can do that, then any problem can be alerted promptly to end users, and therefore problems can be fixed, can be rectified to make sure that the quality of output from flow meters is always at this optimum, and also minimizing the risk of the error from propagating to the system. However, because we're dealing with advanced modeling techniques, which model to use is really highly dependent on the type of data we have. Normally in data modeling, the data can be grouped in two main categories. One is labeled data, one is unlabeled data. If you have unlabeled data, we will need to use an unsupervised machine learning approach. If you have labeled data, then we can use the supervised machine learning approach. So before we go on and me illustrating to you different types of insights and results we can get from advanced modeling technique, it's very important that we, first of all, we know, what do you mean by, label and unlabeled data? What are the difference between them? How can we spot them in practice? The next question will be, well, what are the differences between supervised and unsupervised model? Well, which one should I choose? So in the next couple of slides, this has conveniently lead us to section 3, modeling with labeled data versus unlabeled data. So let's look at unlabeled data first. So in other words, we need to use an unsupervised machine learning model approach. So what do we mean by unlabeled? Unlabeled data has input value, but no response variable. In other words, we do not have information on under which condition those data was collected in. So we only have the diagnostic variable, but we don't actually know, well, are those data collected when the flow meter instrumentation are working fine, or were they collected where we had a fault? We don't have that information. So because of that, it's actually very common to find this type of data in practice. And because of its unsupervised nature, so in other words, we don't do anything with it, the model will operate by itself. It will look at the data and it will do it, and it will monitor the data changes. And we don't really intervene with it because it's unsupervised. Because of that nature, it's actually very suitable for real-time monitoring because of the unsupervised nature. However, because of that, the model is actually more complex with a higher computational cost because we can help the model through its learning process. It does it by itself. And because of that, it's also less interpretable and less accurate because we don't have the response variable. So I'll illustrate now some example to hopefully to illustrate my point better. So anomaly detection is a very well-known classic example of an unsupervised model. So anomaly detection algorithm has been widely used by many sectors, especially in the banking sectors, for fraud detection. So the concept of anomaly detection algorithm is that it will take the data in and then it will break the data into different components. It will break the data down into the general trend of the data, any remainders of the data, any random noises of the data. And within each of those components, the algorithm will try to look for any unexpected trend and an unexpected change, any anomalies within those categories, and then it will produce an output similar here, illustrating to end users any anomalies it has found, and it will flag them up, as red dots. Any healthy data is illustrated as black dot with a bandwidth to indicate that any data within that region is classified as healthy. So then end users can go and, find out exactly what's causing these unexpected spikes and jumps within the data. So find out what's causing those anomalies. Another type of anomaly detection is what we call Bayesian anomaly detection. So again, it's a very similar idea. We will tell the model, we will train the anomaly detection model will look at a set of data, and then based on the data it observed, it will then try to predict or project a region on what the future data should lie within with a 95% confidence interval. If the actual data do not fall within that expected region, then it will alert the end user saying, there's something wrong with it. There's something, the data do not conform with this expected region. So maybe there's something wrong with it. So you should go check it out. So in this particular example, we can see that there's two particular jumps or peaks here, times interval here that do not lie within the plank expected region. So then this will alert to the end user saying that, there's something odd going on between these time periods that's causing these data to not conform with the general trend. So then end users can go and investigate a little bit more to find out exactly what's causing this behavior. So when I say, so what do we mean by when it says it's less interpretable? Well, it's less interpretable in the sense that, yes, an unsupervised machine learning model can tell you there's something weird, something odd is going on in your data, but it can't do anything else but that. In other words, it can tell you, there's something going on, but the end user needs to go and figure out exactly what is causing that jump. So that is probably one of the disadvantages from using an unsupervised machine learning model, but that is something a supervised machine learning model can help to overcome. So in order to use a supervised machine learning model, you will need to have label data. So what we mean by that is that the label data are data that has input variable and output variable. In other words, we have information on exactly when those data was collected. What condition were those data collected? Was those data collected when my meters or instrumentation are working fine? Or were they collected when exposed to error A? Or were they collected when exposed to error B? So we have that piece of information. Now, because we have that piece of information, we can help the model through its learning process. We can train the model to learn all the trend pattern correlation that exists when the flow meter was exposed to different operating conditions. So the model are able to learn all the subtle differences when we change from normal operating condition to a faulty operating condition. So I will be able to pick up those subtle changes, which may be too subtle to pick up if we were to observe it through human eyes, but machine learning model, it will be able to pick that up by looking at all the changes that occurred across all the variable. So it will learn the pattern of correlation using training data, and it will identify any connections between the input variables and the output variable. Because of that, it can perform variable selections. So imagine you have like 60 different variables outputting from your flow meters. By using a supervised machine learning model, it can actually narrow down to the key variable we should focus on if you wish to monitor for a particular type of error. So say, for example, you know that your system is very prone to having wax buildup just because of the activity your meters is performing, then having a supervised machine learning model, it can tell you which are the variable most affected when exposed to wax buildup, so that you can keep an eye out on those variables to monitor for any changes. Because of the supervised nature, this is usually take place on offline. Models are a lot simpler because we can guide them through the learning process with a lower computational cost, and the result is very interpretable, very reliable, and very accurate. So you might ask, well, that's great. Why can't we just all use supervised machine learning model? Look at all the advantages you just list out. Yes, that would be great. However, in order to use a supervised machine learning model or to build a reliable supervised machine learning model, it's actually not very common to find in practice to have a good labeled data, because it requires a good data acquisition system as well as a good data management to make sure that all the data are carefully labeled, consistently labeled. So to show you an example, so a classification model is an example of a supervised model. And next, I'm going to show you a set of results that we obtained by using a supervised machine learning model, the prediction result we get. So this example shown here is based on an experiment data that we gathered with an NEL, where we are interested in looking at the effect of installation error on the performance of our ultrasonic flow meters. So we've deliberately exposed our ultrasonic flow meters to 4 different types of operating condition. The first one is where we have the meter set up in the ideal format. So everything, we follow the manufacturer's instructions, so everything's ideally set up. Next, we expose it to 3 different types of error condition. The first one is where we deliberately set up the meters in a vertical misaligned format. The second one is in a horizontal misaligned format. The third one is where we introduce step change. So because we have information on which condition those data was collected in, we can benefit from using a supervised machine learning model. So what we did was that we then trained the model. We built the model, we tuned the model for it to learn all the different trend, pattern, correlation that exists between all the variables when it's exposed to all these conditions. We asked it to learn all the subtle changes when the meters is performing under normal conditions and under the 3 different error states. So once we build the model, we then feed them 4 different sets of unseen data to test the model to see how it would react if we were to deploy the model in practice. So in a way, mimic how well it would perform if we were to use this to predict a set of data. So if we look at this first set of data, so based on the model, based on the pattern, the trend, the correlation, and learned, with a probability of 0.99, the model is confident that this particular data set was gathered when the meter was under normal operating condition. In other words, everything's fine. We don't need to do anything with it. The ultrasonic meter was set up perfectly, exactly as we want it. Next, however, if we look at another set of data, and here the model predicted with a probability of 0.91, this data set was gathered when the meter was set up in a vertical misaligned manner. In other words, we have a problem because the model has told us that, there is something wrong with this data. This data was not gathered from a healthy meter. So therefore, action needs to be taken. We need to go and fix it because it's been set up in a vertical misaligned manner. So this quick example just kind of in a way illustrates to you the benefits that and the insight we can get from using supervised machine learning models, because not only we can pinpoint whether our flow meters is working normally or whether we have a problem, it can go one step further by saying to you exactly what is causing the problem, what error was causing all those shifts that you've seen in your diagnostic variable. So what are the benefits? So again, we can accurately predict the operating condition of the meters. We can distinguish between error states and normal states. So if you remember, for an unsupervised machine learning model, that's mentioned previously, yes, the model can tell you, oh, there's something going on, we should go check it out. But a supervised model can do one step further by saying, with this probability, this likelihood is because of error A, is because of error B. So we can get one step further. So because of that, it can actually be used to overcome the ambiguity issue that was mentioned at the start of the presentation. End users are no longer comfortable and confused and be like, oh my God, what's happening? I see a drift in my flow meters. What is causing the problem? By using a supervised model, we can help overcome that ambiguity. And because of that, we can improve our fault diagnosis process because then we know, what errors to fix. So next, I would just like to emphasize on the benefit of using data-driven models through 2 different case studies. So the first case study, let us look at the detection of a magnet on a Coriolis meter. So the first case study was on the detection of magnet on a Coriolis meter's outer casing applied in a fuel bunkering industry. So just a little bit background information on the fuel bunkering. So fuel bunkering is the process of transferring fuel from a storage vessel to a receiving ship's fuel tank for consumption. So obviously to ensure that, the correct quantity of fluid is being delivered, everything, all the financial transactions are accurate and traceable, a Coriolis meter is used to measure the transaction. So you may think that's great, everything is set up, so what is there to worry about? Well, however, recently the fuel bunkering industry has recently seen a rise in fraudulent activity where perpetrators have deliberately attached a magnet on the outer casing of a Coriolis meters to undermine the Coriolis meter's measurement integrity. So by attaching a magnet on the Coriolis meter, it's going to affect multiple diagnostic variables for the Coriolis meter. And by doing that, it's actually a criminal offence because it's going to influence the measurement. For example, the seller may ended up selling less fuel than agreed, which can result in the buyer ended up paying more than what is received. It's a criminal offence. It's very important that we catch it. It's very important that we're able to detect it and to stop it straight away. So because, like I mentioned before, a diagnostic variable has multiple interrelationship with each other, by attaching a magnet to it, it's going to affect not just one variable, but it could be multiple variables, and those variables might impact on other related variables. So to really properly, be able to detect this criminal offence, a data-driven model was built for this purpose. So the data was gathered under two conditions, where one is the normal operating condition, so no magnet attached to it, so the Coriolis meter is working fine. Another one is when we have faulty operating condition, in other words, we have magnet attached to the meter. Now, because we have information on when, under which condition the data was collected in, we have a label data. And because of that, we can build the more reliable supervised machine learning approach. So this is what we call a classic classification model, where we wish to segregate the condition and flagged up data which was gathered when the meter had a magnet attached to it. In other words, we want to train the model to learn all the to learn the pattern, the trend, and the correlation exists between variables when the Coriolis meter was normal versus when it had a magnet to it. So we want the model to learn all the subtle changes that we would expect if there was a magnet. So then we can flag that up. So the model was trained and built to find the optimal model and detect this magnet condition. The optimal model had the average accuracy rate of 97.9% with a sensitivity rate of 1. So after we trained the model, we built the model, so the model is in place. We then feed it two different sets of unseen data, to mimic how well it would behave if we were to apply this in practice in order to detect a magnet condition. So here are the result graph shown on the right-hand side. So if we just look at the first set of data, so based on the pattern, the trend, the correlation, all the subtle changes and variables observed by the model predicted with a probability of 1 that this data was collected when the Coriolis meter had a magnet attached to it. In other words, we have a faulty condition. Now we need to go take action and remove the magnet. Similarly, when we now look at another set of data, in this case, with a probability of 0.939, this data was collected when the meter did not have a magnet. So it's highly likely that, the Coriolis meter is working well. So in other words, no actions needed. We don't need to send someone out to remove anything. So through this example, I hope that you can see that, by using a supervised machine learning model, it can really help end users with their fault diagnosis process, because it can indicate whether we need to take actions to fix a problem or whether everything is working fine. So then we don't need to waste our time and effort to, fix something that doesn't need to be fixed. The second case study is now on another type of meter, the ultrasonic flow meters. And in this case, we wish to use the model to detect when we have an unwanted second phase in the fluid. So as we know that the presence of an unwanted second phase in a single phase fluid can really affect the accuracy and the reliability of a flow meter's output data. So in order to investigate, the degree of effect, how badly were our ultrasonic flow meters affected by having an unwanted second phase, an experiment was conducted with an NEL where a different percentage of gas was deliberately injected into the fluid to investigate the subsequent effects on the meter's performance. So we have gas volume fraction ranging from 0% to 0% GVF to 10% GVF. So similar to before, because we know under which condition our data is collected in, we have label data, and because of that, we can build a supervised machine learning model. So the model was built through learning all the subtle changes when we changed the percent of GVF from 0% to 10%. We asked it to learn all the subtle trend, differences, correlation, exist between all the variables. So once the model is tuned and built, again, we then tested it by feeding in a set of unseen data to see how well it will cope, if we were to use this in practice. So, the supervised machine learning model was built and trained to distinguish different percentage of GVF based entirely on the trend pattern correlation variable, and this model had an average accuracy rate of 86%. So here are the results from the unseen data. So do we have an unwanted second phase? In this case, yes, because this data, the model predicted this data with a likelihood of 0.191% was gathered when the ultrasonimeters was exposed to 0.10% GVF. In other words, we have a problem. There's gas present in the fluid. We need to go and do something about it. So not only we have this piece of information, the model is also capable of producing probability for the other operating condition. For example, we can look at, well, what is the likelihood of, this data to be collected when the meter, just have single phase flow, in other words, 0% GVF? Well, the probability, the likelihood of this is only 0.0067. So the chances is quite slim. And similarly, if we say, well, what happened? Maybe we don't have 0.10%, maybe we have 0.20%. Well, the probability of that happening is only 0.075. So as you can see that the most likely probable cause for the drift seen is due to having 0.10% GVF in your system. So again, in this second case study, you can see that by using a supervised machine learning model, it can really help us pinpoint with greater certainty on the exact cause of error that's responsible for the drift seen in diagnostic variable, so that it can really improve our fault diagnosis process. So time is not wasted, fixing something that doesn't need to be fixed. So these are the two case studies to illustrate the benefit from using advanced data-driven model. So next, I would just like to conclude today's webinar off by just giving you some conclusion and some quick summary on the stuff that we mentioned. So as the world moves further towards digitalization, more data is being produced than ever. I mean, everywhere you see in media now is talking about big data, big data. So, in order to unleash the insight and benefit from big data, why is big data such a buzzword? It's because by using appropriate technique, we can extract values from big data. So really, to prevent the data from becoming, just the new plastic, just sitting there doing nothing, we really need to use advanced modeling technique to unlock those values. In today's webinar, we talked about, different modeling techniques that's available to extract various levels of insight from data. So for the purpose of this webinar, I have grouped them into three categories: basic, intermediate, and advanced. And as mentioned before, depending on the level of modeling techniques you use, you may require certain requirements from your data. The more advanced your model is, the more requirement you need from your data. We've talked about, how we can identify labeled data and unlabeled data, and how what kind of model do we use to model them. So for labeled data, we can use the more reliable supervised machine learning approach. For unlabeled data, then we can only use the unsupervised machine learning model approach. Two different case studies were used to demonstrate, the type of insights and benefit that can be obtained from using advanced modeling techniques. For example, we can use it to detect known or unknown error to really improve our fault diagnosis process. We can ensure that any errors are flagged up promptly, fixed promptly to minimize the risk of error propagating through the system. And obviously, it will help us in terms of decision-making process, because it will let us to know whether we need to go and fix a problem or whether everything's fine. There's a type of models that we can also use, which will tell you how many years of remaining useful life you have in our flow meters. So then you can give you valuable information as to, well, when do I need to replace the flow meters, or can I get a little bit more years out of the useful life for my meters. It can obviously reduce costs as well as minimize any unexpected downtime. And most importantly, it can overcome the drift ambiguity by using the model to help us pinpoint the type of error with greater confidence, because how can you possibly go fix something when you don't even know what's wrong with it? So I guess just, a final saying, like a sort of like a take-home message would be, storing data is simply not enough anymore, because in order to unlock the value, the benefit from data, you really need to use advanced modeling technique to unlock it, because you can then benefit from all this great insight that you can get from this. So that is all from me today. Thank you very much for your time listening to my webinar, and I'll be happy to take any questions. Thank you.
Thank you, Yanfeng. We do have a few questions that have come through, and we do have a bit of time left, so I'll run through a few of these. The first one is there a standard procedure we should follow when we do data modelling?
Thanks for the question. So yes, there is a standard procedure we normally do. So usually when we get a set of data, the first things first we do is that we really need to understand what kind of data we have. So this is why at the start I introduced the basic modeling techniques, because the first thing we need to know is that what is our data distribution like? How many variables do we have? Do we have any missing values? Because if you have missing values, the first thing you need to do is probably to remove them, because certain modeling techniques cannot cope with missing values. So then the first thing first when you get data is to even just very simple plot some graph to see what's the general trend of your data, get a feel on what the data is telling you. Because through that you'll be able to find out problems such as missing values, or if you have a column that's constant, then because it's constant value, usually it doesn't add much to it doesn't give much values in terms of data modeling, then you can remove that, so it's less work for your models to do. After that, so once you cleanse your model, cleanse your data. So once you cleanse your data prior to performing any data modeling, the next things you will want to do will be to say, well, what is it you're trying to do? Are you trying to make predictions, and then, or whether you try to predict a type of error? Then based on that, you would then decide which kind of modeling techniques to use as well.
Thank you. And another question. On one of the slides, you mentioned about the optimal model. How do you choose your optimal model?
Right. So, so in one of the slides, I've mentioned optimal model is because even when you're talking about a supervised machine learning model, and under that we have the classification model. Even for classification model, there are many different types of classification model that people can use that can achieve the same type of outcome. In other words, predicting the type of error. However, each of those models have their own operating principles. So in a way, they can modeling principles. So then they all work slightly different. So it's very important that we tried out lots of different of these models to see which one performed the best. So for that examples, obviously to see how well your model performed, we have the very common general prediction accuracy. So a good model should be the one that has a high prediction accuracy rate. On top of that, another way you can use to decide which one is your optimal model is look at other measuring metrics, such as the sensitivity rate or the specificity rate. So in other words, your true positive rate and your true negative rate. And depending on the aim of your, depending on the objective of your problem, some people may favor, say, the sensitivity rate over the general accuracy rate. But an optimal model should be the one that performs well across all metrics. So for example, but see if you were in a dilemma when you say you have two models and both of them, perform quite similar. So how do you choose which one is the optimum one for that situation? Then you will, then you need to think, well, see if my aim, so if the risk of not detecting a positive case is going to lead to a detrimental effect, for example, the failure of detecting an error in the aircraft or failing to detect a cancer in a patient, then you may want to look at the sensitivity rate to make sure that a model is able to predict with a high sensitivity. So yeah.
Okay. And there's another question. Is there a particular format the data needs to be in for data modeling?
The data doesn't need to be in a particular format. So we've worked with data that's comes in all sorts of different formats. For example, we have ones that's coming in Excel or CSV file. We have one that's coming in text file. We have one that's coming in the form of database. So with nowadays, like a lot of programming language is able to cope with data that's in different formats. So really, we don't have a particular format for the data that we need to use in order for data modeling. As long as the program can read it, as long as everything's well structured, then I think it'll be fine.
Okay, I think we've got time for one more question. Last one. Is there a standard model that we can always use for a particular situation?
Thanks for that question. So that's a very interesting question. I actually wondered this myself when I started data modeling, but a short answer is unfortunately no, because different types of model will behave differently under different conditions. The reason being is that the performance of your model is highly subjective to the type of data you have. And data, it really changes for different end users. So you can't exactly say that, so you can't really have a one golden model that applies all, because there will be in some cases where a model will perform better in predicting one error, and there'll be another type of model that actually performs better when you predict another error. So one advice I would give is probably when you start off with data modeling, you can always work with a baseline model. And from that, you can then see how well that baseline model performs. If it, is kind of in a way underperformed, and after you're tuning it, improving it, it still doesn't really quite improve, then this is where you can look at another type of model. One advice is that I will try not to overcomplicate your model at the first time, because a lot of people seem to think that because the problem I'm trying to solve is very complicated, my model needs to be really complicated as well. Sometimes it's not like that. Sometimes you can actually get a better result by using a simpler model. So my advice is that, unfortunately, there's no one golden model, but you can always start off with a baseline model and then work your way up by adding in more parameters to make your model more realistic or better.
Okay, thank you, Yanfeng. And again, to everyone, thanks for joining us today. As I mentioned earlier on at the start, we will be sending each of you a copy of the presentation and recording. If you've got any further questions or information, you can contact us or feel free to visit our website at www.tuvsud.com. And on behalf of myself and our presenters, thank you for taking the time to join us today. Enjoy the rest of your day.